One more time. The chapter 1, there'll be about 8 questions about the vocabulary words in chapter 1. And I'll even show you, we'll have a review day. Thursday's a review day where I give you a piece of paper and actually tells you all this stuff, okay? And then the demonstrations that I did, I want to review those a little bit. I even have some more demonstrations today and tomorrow and the next day. And then one of the biggest parts is this stuff here about Michael Faraday and the candle experience here. I'm hoping, I think it's going to work, that Thursday, the second half of the period, I'm going to get you in groups, and I'm going to give you a list of about 20 to 25 vocabulary words, science words, and you're going to sit down as a group and write out the story of how a candle works. And we can do that. We can start that by reviewing yesterday's lesson. And so your goal eventually would be able to write out the story of how a candle works by using words. So let's look over here. Do you ever have the article with them? If you have your article out, I've been writing all over mine. Of course, I'm teaching with it, but you also should be writing on yours to remind you about different things. Now, I read the first 3 paragraphs and just kind of talked about he was kind of a curious person, and he did eventually become a physicist, a physics professor at MIT, but that's how curious he was. Sometimes I feel like some of the top physics people in the country they never really grow up. They actually keep asking the questions like kids do. Kids make the greatest scientists. They keep asking questions. It's only when you get a little older that you figured out that certain teachers or somebody, your parents said, don't say that. That's not right. You're wrong. That's unfortunate because you should be still asking questions. But some of you have kind of got squashed a little bit and you don't ask as many questions as you should. And there's peer pressure, isn't there? Ooh, what do you think? What's somebody going to think of me if I ask a bunch of questions in class? I'm sorry that you feel that way. But anyway, some people don't do that. They don't get, and they keep asking questions, and they become physicists. Some of them. All right. So what do you remember? Let's go ahead. Let's start using some vocabulary words. Paraffin. What's paraffin? Ready? Go.
That's like the carbon compound, and
it is a carbon compound.
And it has to do with like the wax.
It is a wax. Go ahead. Keep going.
It raises the melting point of the wax so that the
that's another chemical, not paraffin. That's called stearin.
Oh.
So stearin was something that they added to the paraffin to raise the melting point. What else?
It's very like all waxes like they melt. I mean they burn.
All right, and not only do they burn, but that whole class of compounds. What do you call the class of compounds that only contain carbon and hydrogen?
Hydrocarbon.
Hydrocarbons, right? And all hydrocarbons do burn. What do you mean in chemistry when you say burn? Yes. Yes. It's always a chemical change. Burning is always a chemical change. What's the word organic? How's that going to fit into our story? Is paraffin organic? Yeah, carbon compounds are organic, aren't they? So all hydrocarbons are organic, aren't they? All right. Stearin. Stearin raised the melting point. So what? What's that supposed to do?
It makes the candle last longer.
Okay. I had a student, he emailed me yesterday. He was kind of excited. He had researched it, and he actually found, and he's going to turn it in, and he actually found a person who discovered stearin and its properties. And I haven't read the article. He hadn't given it to me yet, but I'm hoping it's going to tell me that he actually tried to mix it with paraffin or whatever. I don't know who first did that. I don't know. All right. Then, let's see. We started talking about the wick, didn't we? Oh, wait. I know. Where does the oxygen come from for burning?
Air.
Well, what part of the air is oxygen?
20%.
Only about 20%, right? You got that? Okay. Let's go to the wick. The wick, there's a fancy word called mordanted, but you probably heard the word pickled. Have you heard pickled at all? You chemically treat the wick. Who did that? No one's looked that up yet. Who's the first person to figure out if you chemically treat the wick, it'll do what? Now, read again. See what it says. It does do something to the wick, but not necessarily burn longer. What is it?
It burn too fast and it wouldn't smoke.
It wouldn't smoke. Okay, so that means for a long, long time, candles, when you lit them, they always gave off black smoke, right? Somebody figured out if you do this, you're not going to get black smoke. Another thing on the second page, it said, if you pickled it, what else did it do? Down there at the top, it said it was ashless decomposition. What's that mean? Yes.
Like maybe when you look at your wick, you can see that it like turns black, but it doesn't like start like flaking off everywhere. Or something.
Yeah, in asphalt, right? Both of my parents, and back then, both my parents smoked, and I didn't, and I never did want to smoke. But back then, lots and lots of people smoked. It was big. It was too big, and I clearly remember them when they'd light a cigarette and they would, smoke. There was ashtrays around the house, and why do you make an ashtray?
Prevent the ashes.
For ash. And if you just set that cigarette there and didn't take a puff for a while, it would keep burning a little bit, and sometimes the ash would get longer and longer, and then they tap it out. But anyway, that's what happened with candles. The wick would burn, part of it burn, and turn into an ash and fall over on top of the candle or wherever else. All right, so we got the story now? Are we getting down there? Let's go down some more. What did they say about, why would somebody want to have a double boiler? Why would you want to do that? Why is heating wax a dangerous thing? Like if you wanted to get, yeah, go ahead, Libby. Look.
Because when you heat wax and it turns to a liquid, it turns into a gas, and then the gas can like light a flame and start a fire.
That's right. You let that gas come and mix with the air, and then a spark. That would be a real dangerous. Let's say you had a campfire. Don't do this. Don't ever do this unless you tell your parents. If you had a campfire and you had a block of wax and you put it in there, eventually it would melt and turn to vapor. And I don't know. Would you get a big explosion? I don't know. You could get a pretty big explosion. Possible. I've seen people do. You ever seen these turkey fryers?
Yes.
All right. So these people do. Oh, that's the best turkey in the world. That's Jim Gaffigan. You ever heard? That's the best turkey in the world. And anyway, and they take these frozen turkeys and they put them in this oil that's been heated up really hot. All right. And so what happens? It'll splash, right? And the cold turkey, and it'll start to bubble out, and then the bubbling grease hits the fire underneath it, turns to a vapor, and all of a sudden you got this great big fireball like that. Okay, let's go on down. What about hydrocarbons solubility? What do you think about that?
Aren't they like insoluble
In what?
in water?
That's right. Do you know the soluble in gasoline, though? If you wanted to mix candle wax with gasoline or rubbing alcohol, it probably would mix, but not with water. So it's insoluble in water. Let's go down here. What happens? Did we read this much? Tell me if we got that far. What happens if you have a really too small of a wick for your candle? Okay, Tim.
The flame won't maintain, it can't maintain the flame.
It might make a really weak flame, and that flame might even go out, right? What about if you have too big of a wick? I'm looking for people who haven't raised their hand yet. Yes?
It'll result in a smoky flame.
What is it? Smoke, right? Smoky candle. So you never thought, I never thought about that. The wick has to be the right size for the candle. Anybody have an idea so far about why a small wick would be a weak candle and a big one would be smoky? You have an idea already?
Yeah, I think because when we talked about like the wick sizes, it's talked about like how many fibers are like twined together or whatever it is, wound together in order to make the wick, and so like the more there is, it's gonna like create like a flame that like gives off like a bigger.
Why would it be smoky though if you have too big a wick?
It's actually like, I guess because it's actually burning it rather than because it can't.
It is burning it.
Pickle it through all the way or something.
Okay, you're getting close. You're getting close. Anybody else? Will?
There's not enough capillary action.
So we haven't even talked about that, have we?
How do you know that? Because he's reading ahead.
How do you know that?
We did that yesterday. We went through that section.
Okay, all right. Anyway, it does have to do with how much oxygen can get to the fuel, and we're going to talk about that some more. Okay. Now, do we read the part where it says Faraday? Did we do that yesterday? I can't.
Yes.
Okay, so, all right, let's go down here. I might ask you on the test, I might say about when are you talking about Faraday doing these things? Now, he did it He did the experiments probably a little bit before this, but I would give you a 20-year period. When did Faraday do this stuff? 1900, 1700, 1600, 1650. What do you think?
1660.
That'd be close. Okay, and he gave the lectures. Said 1860. Did you say 16? 1860, around 1860, 1861, he gave the lecture, so he must have done the experiments maybe before that. So somewhere around 1850, he may have done some of these experiments like that. Now, one of the things you're going to have to do, go down to the last paragraph, is tell me the story about how a candle burns, how it works. And number one, it says, the heat from the wick does what? Tim, put your head up, please. Heat from the wick does what?
What page are
Down here at the bottom.
Melts the wax.
Melts the wax. That's important. Change it from a solid to a...
Liquid.
Okay, but the flame never touches the solid candle. The flame never touches the liquid candle. So what's burning?
The wick.
The wick?
No.
The wax goes through the.
Okay, we're getting there. But then it said, why did I need to melt the candle, the wax? Why did I need to melt the wax?
To get the vaporized wax in order to create.
Well, then let's throw the wick away and let's just vaporize the candle right there. How many of you tried to make a candle with just wax? How'd it go?
It just turns black.
did it act like a candle?
No.
Why not? Didn't you vaporize some of the wax? I bet you did.
Because it's not a
Can't burn itself.
hydrocarbon, so it can't burn.
No, it is.
It is.
Wax is a hydrocarbon. But that's all right. That's what we're doing here, right? We're trying to figure out the story. So it said here, the heat melts it, and then what? What's the second thing it says?
Melts the wax.
The liquid is pulled up
Into the
by what?
Like
Capillary.
attraction.
Now, did I do any demonstrations yesterday with you?
No.
Okay, so that's time for me to show you what that means, okay? So I have here
Let's make-
a glass petri dish, and what I'm going to do is put something that's very visible so you can see it. So I'll put some red food coloring. Everybody can see that, right?
Over there.
Okay, wait a minute. Wait, you can't see anything. Ah! Did I have that off?
Yeah.
I am so sorry. You should go like this. No, I mean, okay. When you said what paragraph I'm on, I saw my monitor showed but I didn't. Sorry. Sorry on the video. Okay. All right. Everybody ready? So now, guess what I have? I have this little tiny glass straw. Anybody have an idea what name they give these little glass straws? These are capillary tubes.
Capillary tubes.
Wow, capillary tubes. What's that? How many of you have ever gone to a doctor and they did something? They pricked your finger and put a little glass tube next to it.
I do that a lot.
All right, and the little glass tube. And why does that blood go up in that tube?
Capillary tract.
That's right. So anyway, I'm going to show you here. I'm not going to suck on it or anything. I'm just going to lay it there. It's just a glass tube. Just going to lay it there and okay.
A new color.
Anyway, so again, I didn't do anything. I just laid it there, and it's seen to. Why would it want to go uphill? Why would water want to go uphill? And anyway, I'll show you what that. I'll show you what that means. The common name for this is called wicking, but it's actually the scientific name is called capillary attraction. I think Faraday called it capillary action. Another word is capillarity. Anyway, capillary attraction has two parts to it. One of them is called adhesion, and one is called cohesion. And I'll show you how to memorize which is which. Adhesion is the science word that means that two different materials are attracted to each other. Cohesion means the same material attracts itself. Have you ever heard these words before?
Yes, biology.
Okay, good. Well, anyway, adhesion, if you think about it, what's another word for Scotch tape or masking tape? What do you call any kind of tape that kind of sticks to things? Adhesive tape. There's even adhesive Band-Aids, aren't there? Anyway, and so I used to, when I first started this, I said, oh, I always mix those up. Which one's adhesion, which one's cohesion? So I'll show you a little memory trick, okay? What are the first two letters of the word adhesion? AD. So I told myself, hey, that's great. If the two materials are different, AD, get it? If the two materials are different, it's adhesion. If the two materials that attract each other are different, it's adhesion. And then cohesion must mean the same material. So what's happening here is that the water was attracted to the glass, and the glass is attracted to the water. What do you call that? Adhesion. But then, as it had pulled the water up, the water attracted itself, didn't it? That was cohesion. Do you remember when you, and we'll do this in the next chapter, but when you use a graduated cylinder, maybe you did this in middle school, you should have noticed that when you put water in that graduated cylinder, it formed like a little bowl. And the teacher probably wanted to teach you that word called meniscus. Do you remember that word, meniscus?
Yeah.
And you had to learn to read the bottom of the meniscus. Now, why did a meniscus even form? Because the water is in contact with the glass here, right? And at the top, it's only attracted. Only at the top is where the top water is attracted around that little ring, isn't it? So the ring gets pulled up, and then it pulls water down here up and makes like a bowl. So that's capillary attraction also. And what's interesting is you might say, why are you showing me this when I don't think a candle wick has a bunch of tubes in it? Do you think it has a bunch of tubes?
No, but it
Good.
has those little.
It could, but I don't think so. So we'll do another thing. How about paper towel, or I use, in this case, tissue paper. How about that?
Adhesion. And truth.
Both. As a matter of fact, it's kind of like a cartoon. It's like, whoa, what's making that thing do that? And every time you use a towel, or every time you use a paper towel, that's what's happening, isn't it? It's capillary. So instead of tubes, you can actually have fibers laying next to each other. Okay, that's pretty neat. What if I take two capillary tubes and I don't put any liquid in the end of them? What if I just put it on the outside? What if I just put it right here in the middle? What's going to happen there? Uh-oh. I'm just going to put it in the middle. Not only does it climb between the two capillaries, but the capillary in the petri dish forms two surfaces, doesn't it? And it's crawling along there. Adhesion, cohesion, like that. And it's called wicking, or capillary attraction. Everybody see that? That's a big science thing. That's pretty big. So, it's still going, isn't it? Do you ever wonder how do leaves in a plant get water? You think, well, the rain falls on the leaves, and they can't get water from there. It has to get it from the ground, doesn't it? So it has to get into the roots, and then what?
Capillary attraction.
It is.
Sucks it through the veins.
I don't know about sucking.
Not suction.
I'm not sure, but I do know.
There's no sucking.
I do know there's capillary attraction, right?
Yeah.
Yeah,
As a matter of fact, it's pretty powerful. It's pretty powerful. I know probably in elementary school or middle school, you probably did this before. You take a piece of celery and you cut it, a new cut, and you stick it in some food-colored water. You can do that tonight. You have any celery? make a fresh cut. Put it in some like dark red or dark blue food coloring, and just wait for a while. And all of a sudden you say, "Wow, the leaves are blue or the leaves are red." Well, those little things that people don't like with celery, little strings, those are tubes. Those really are capillary tubes, aren't they? And that really does. It'll make it all the way up to the top of those leaves, like that. All right. I'm going to try something I have never tried yet, and I thought about it. I'm going to do something kind of weird. I'm going to take something that has no tubes at all. Okay, now, what I'm going to try to do, if I can push this together. All right, what do you think? Is it possible that you could get wicking or capillary attraction when there's no tubes?
Yeah.
It's just particles?
If you put a drop of blood on it.
Well, this is food coloring.
Wait, you
I,
use
I,
human blood?
I, Yeah, I took some. Yeah, but
What?
Little
Best
Nas.
buddies.
Little babies.
Little Nas X.
did a little bit.
Low.
Wait, keep watching it. Look down here. Even when there's very little salt down here, it still seems. It looks like it's working its way out there. I'm gonna do one down here.
So what's the cohesion part? Like I know the adhesion because the drop of food coloring is attracted to the salt, but then what's the cohesion?
Okay, so the water would be attracted to the sides of the crystals, right? And then the water would also pull water. Water is attracted to itself, so it pulls itself.
That's how it spreads.
All right. Ooh, that's
It's
kind
like
of
when you
neat.
have two droplets of water like next to each other, and then like they reach each other, and then they like.
Or just the fact that a drop of water itself forms a little bulge, doesn't it? It attracts itself, doesn't it? All right. Well, anyway, now we know a little bit more. And by the way, this is called wicking. If you know anybody who is a home builder or they fixed houses, you say, "What's wicking?" They'll know it just like that. They won't call it capillary attraction. They'll call it wicking. And wicking occurs all kinds of places. How about the beach? You think wicking could occur at the beach?
Yeah.
It's interesting, isn't it? Sand. Interesting.
Oh, when lightning strikes the beach and there's no rain, it makes like a tube of sand.
I have heard of people, if lightning happens to strike the sand, it's so hot it kind of fuses the sand together in the glass.
Yeah, it's like heat ledge.
Right. So, and by the way, everybody has grown up using the word heat lightning. I have no idea what that is. I heard it myself, but I can tell you, heat lightning means that lightning is so far away that it just makes a little glow. And I say, if I was over there, I wouldn't call it heat lightning. But we call it heat. That's just. I remember my grandmother using that. I remember my mom used that word, heat lightning. Oh, it's heat lightning. Oh, what does that mean? What if we go over there? What if we go really far over there where it's at? Ah, it's lightning. Okay. But I will say lightning does heat things up. Yes, if it strikes. But anyway, all right, let's go on. So we said here, the heat from the wick melts the wax, and the wax is pulled up by capillary attraction, which is to say the attractive molecular forces between the wax molecules and the wick molecules pull the wax upward. Now here we go. Once the wax climbs near the top of the wick, what happens?
Vapor.
What? I thought it already changed from a solid to a liquid. Now it's going to change from a liquid to a...
Gas.
Now, the release of hydrocarbon molecules plays a variety of roles in the flame. So let's have somebody read. The flame is interesting. All right, I got 2 volunteers. Anybody who didn't read yesterday? All right, Reese, thank you. I'll get back to you guys.
Thank you.
The flame has the interesting features I noticed as a child. Just above the wick, you see a dark cone that is topped by the yellow region responsible for most of the light. On the sides of the flame and near the wick are the blue regions. Depending on the diameter of the wick and the height of the flame, the blue regions may be only a fraction of the height of the flame or may reach nearly to the top of the yellow region. It is surprising that the vaporized fuel molecules give rise to these 3 distinct regions instead of a single region of uniform color.
All right, go ahead. One more.
In the modern classification of flames, the type of flame produced by a candle is called a diffusion flame. Another familiar type is called a premixed flame. Its commonest examples are seen in the Bunsen burner and the gas stove. In a diffusion flame, the rate of combustion is determined by the rate at which the gases diffuse through each other, whereas in a premixed flame, the gases are mixed prior to the burning and rate of combustion depends on the flow rate. For example, stove gas is mixed with air before it reaches the burner outlets. Further classifications of flames include the possibility of turbulence, but here I consider only a non-turbulent diffusion.
All right, it's new science here. It says here that there are 2 kinds of flames. One's called a diffusion-fed flame, and what's the other one?
Pre-mixed.
Pre-mixed flame, right? So, how many of you have seen a gas stove work? You've seen it. How many have it at home? You have a gas stove. Okay, good. How many have never seen a gas stove? Okay, good. When you turn a gas stove on, what does the flame look like?
It's like clicking, then like it's like kind of blue.
Yeah, it's blue. How come your candle wasn't blue?
It wasn't that hot.
Part of it.
Was it heat? Was it the amount of heat? It's a good question. I like what you said.
What fuel is being used?
Okay, now, even though it's a hydrocarbon fuel, it is a hydrocarbon fuel. Here's the difference. Before that burner ignites anything, the gas is actually mixed with a certain amount of air. And they mix the air and the fuel together. You remember that demonstration I did with a great big bottle? Did I do that with you guys?
You could do the fire one.
Yeah, remember that one? Okay. I took a little bit of rubbing alcohol and I went like this and I was hoping to vaporize some of the alcohol. And I also wanted it to mix with what? With the air. And now, that mixture, then I could ignite it. And a lot of that was kind of a blue flame, wasn't it? There might have been some yellow, but a lot of it was blue, wasn't it? A premixed flame has enough oxygen to burn the fuel. Yes?
Like, is that like when you like weld and like you try to explain like why you almost
Want to say it again?
you like weld and you like get the flame like moving?
Okay, now, welding's a little different. Are you talking about welding, are you using oxygen to weld with?
Yeah.
Okay, because they have these things called oxyacetylene torches. Are you talking about that?
Yeah.
Okay, have you done that?
I haven't done that. No.
That's incredibly hot. They force pure oxygen with this fuel, acetylene, and they get these tremendously hot flames. If you'd done that, I'd be very impressed. If you'd done,
You get bonus.
okay. So anyway, you're right. Those had to be pre-mixed. Those are pre-mixed flames like that. An automobile, the carburetor mixes vaporized gasoline with air. And if the carburetor is doing its job right, it has just the right amount of air to explode. Now, what about the candle then? The candle, is it a pre-mixed flame? Did we take the vaporized fuel and mix it with air and then throw it into the fire? So what would you classify it then?
Diffusion.
What about a campfire?
Diffusion.
What about a match? Everybody with me? So, guess what? What makes a diffusion-fed flame different?
It gets the air after once from like where its surroundings.
All right? It can only get air from its surroundings, right? And how fast can it get the oxygen? What is the rate at which oxygen will come into the flame? And whatever that rate is it enough oxygen to burn all the fuel? And I'll give you a clue. If it was, it would be blue. If it was enough oxygen to burn all the fuel, it would be blue. Any ideas here? Where did you see the blue part of the flame?
Closest to the way.
See that? And so as the heat makes everything rise, like here, and it gobbles up some oxygen here, new air comes in, doesn't it? New air comes in from the bottom, and that's where you get most of your oxygen, isn't it? But what happens in the dark zone? What do you think happens in the dark zone? What's in the dark zone? And I did a little experiment with you, and I may be running out of time today. No, I got it. Remember the experiment I did? I may have to light this for a while. All right, everybody see that? I'm gonna see if the video people can see it. No, maybe not.
Here it is.
How about that? Okay, thank you. Thank you. Thank you very much. I like you guys. Oh, wait. Oh, okay, I see. I see. Okay. Okay. Anyway, so what I did is I actually took a glass eyedropper and I went into the dark zone and I took some of that gas out. Come out and push it. So, what do you think is in that dark zone?
The
Oxygen.
fuel, no, it's the
Fuel.
fuel, the wax that's been.
Vaporized, yes. Vaporized wax is in that dark zone. Is that right? What do you think? Now, we have a question that we have never answered yet, and I don't think anybody in our lab answered it. We have some more to learn here. So, the blue zone looks like air is coming in and diffusion. How fast can little molecules of oxygen get in there? And if you remember biology class, diffusion is, what is it? The movement of molecules from areas of higher concentration. See, once you use up my oxygen here, what's the oxygen concentration around the flame? It's 0, isn't it? So the oxygen is going to, wait, I'm getting there, and they bounce around, and eventually it gets there, doesn't it? But it can only diffuse at a certain rate. It can only come in at a certain rate. Do I think that there's enough oxygen to burn all that fuel? And the answer is no.
What is that? What do you mean the burn?
Okay. What is it?
What do you mean the burn?
Because it will be blue. If
Okay,
it
now,
was a-
it'd be all blue. Now, another thing that's interesting is I'm going to put this in the yellow part of the flame. What do you see there?
Smoke. It pushes it away.
Okay, and not only did I see smoke come out, what is right there? What do you think that is right there? They call it soot. What do you think it is? I'll give you a clue. It's on the periodic table. Carbon. This is carbon. See that? It's carbon. Now, where do you think the carbon's coming from?
The evaporation.
Hang on. If you vaporize a hydrocarbon, you get a hydrocarbon that's a gas, don't you? But it's still a hydrocarbon. But that's just carbon. So what's happening to the fuel? Is any of the fuel molecules, do you think they're getting broken up?
No.
Then how am I getting carbon?
They are being broken up.
They are getting broken up.
But
Some of the CH molecules are being broken up into C. And I know you're not going to believe this, but here's a question that none of you asked. Why do you see that flame? Why do you see the flame? When I have a gas burner on, I see a blue flame. But why do I see this bright yellow flame? And the key is right there. It's that stuff right there. And what is it called again?
Carbon.
Or soot, isn't it? Well, it's black. That's not black. So we have a new word for you, okay? It's called incandescence. Have you ever heard the word incandescence? Unfortunately, your generation will be one of the first generations that will, almost every light bulb in your house will not be incandescent. An incandescent light bulb is around for over 150 years. You screw it in, a little wire, there's a little tiny filament wire in there, and you force a whole bunch of electricity through a little tiny wire of tungsten. And it got so hot, it would incandesce. What's that mean?
Light up.
It would glow. I used to think, people are funny. I mean, I know all of you don't have any egos, do you? Well, maybe. I didn't know I had an ego. I just thought I was a little bit smart. I was okay. I'm kind of smart. Anyway, we don't know that. When you get older, you'll know that's just an ego. But I used to think, when the teacher said, well, the speed of light is so fast, you can't even comprehend it. Okay, what did I think?
Yes, I can.
I went to the light switch and went, what's that light? Yeah, I saw it. I saw that light go on and off. You ever done that?
Yes.
Okay, but you know what's really happening? The glowing piece of wire, just because I shut the electricity off, it was still hot, wasn't it? It took a little while to cool up. I remember another day, I was laying down on the carpet. I clearly remember this day. And it was sunny out, and part of the curtain was open, just a little bit, and a beam came in, right? And I'm laying on the carpeting, and I don't know, I must have moved. And I remember the teacher saying, the atom is so small, you can never comprehend just how small it is. And I remember sitting there, And you know, that light came in, and I saw the smallest little particle I've ever seen in my. I can see atoms. You can't, but I can. What was that?
Dust.
Dust. But you know what? That's we're all kind of like that, aren't we? In a way. And I'm going to tell you right now that carbon, when you make carbon really, really hot, you know what it does? It incandesces. You would not see the flame if it weren't for this right there. All right. Now, I got to watch my time here.
What is incandescence mean?
It means you got so hot that you actually give off light. You actually glow. All right, I got to stop. All right, we'll have some more demonstrations tomorrow, and we're going to kind of wrap this up. We're going to kind of wrap this up tomorrow, and I'll start doing some review.